Welcome to the first learning outcome, where we get to grips with direct current circuits. We'll look at charge, current, voltage, resistance, and power, and how they all fit together. Let's make a start. Let's begin with the basics. In a direct current circuit, current flows steadily in just one direction, driven round the loop by a source like a battery. What's actually moving is charge, usually electrons. And for any current to flow at all, you need a complete, unbroken path. You'll find DC circuits everywhere, in torches, phone chargers, and car electrics, and we measure the current in amps using an ammeter placed in series. Before we go further, let's get our vocabulary straight. Charge, symbol Q, is the quantity of electricity measured in coulombs. Current, I, is the rate at which that charge flows, measured in amps. Potential difference, V, is the energy transferred per coulomb between 2 points in volts, while electromotive force, or EMF, is the energy per coulomb a source supplies. And resistance, R, is the opposition to current flow, measured in ohms. Here's the first relationship worth committing to memory. Current is the rate at which charge passes a point, so current equals charge divided by time. Rearrange that and you get charge equals current times time. 1 amp simply means 1 coulomb of charge flowing past every second, and 1 coulomb is an enormous number of electrons, about 6.24 times 10 to the 18. Just remember to convert any minutes or hours into seconds before you calculate. Let's put that to work. Suppose a current of 2 amps flows through a lamp for 5 minutes, and we want the charge that passes. First, convert the time. 5 minutes is 300 seconds. Then apply charge equals current times time, so that's 2 amps times 300 seconds, which gives 600 coulombs. Straightforward once the units are right. Now let's tease apart two ideas that are easy to muddle. Electromotive force is the total energy a source gives to each coulomb of charge, whereas potential difference is the energy delivered to a particular component per coulomb. Both are measured in volts, where 1 volt is 1 joule per coulomb, and you measure them with a voltmeter connected in parallel across the component. One subtlety: real sources have a little internal resistance, so under load, the potential difference sits just below the EMF. This is one of the cornerstones of the whole unit. For many conductors, at a constant temperature, the current is proportional to the voltage, and Ohm's law captures that neatly. Voltage equals current times resistance. Rearrange it, and current equals voltage over resistance, or resistance equals voltage over current. A component that obeys this is called ohmic, and its voltage-current graph is a straight line through the origin. Let's try a quick one. We've got a 4 ohm resistor across a 12-volt supply, and we want the current. Rearranging Ohm's law, current equals voltage over resistance, so that's 12 volts divided by 4 ohms, which comes to 3 amps. Nice and clean. When components are joined end-to-end in a single path, we call them series. The key feature is that exactly the same current flows through every one of them. To find the total resistance, you simply add them up. The total equals R1 plus R2 plus R3, and so on. The supply voltage gets shared out between them, with the larger resistors taking the bigger share. Think of old fairy lights wired in one long loop. Parallel is the other arrangement, where components are connected across the same 2 points. Now each branch has the full supply voltage across it, and it's the current that gets shared between the branches. Combining them is a little different. 1 over the total equals 1 over R1 plus 1 over R2, and so on. A handy sanity check is that the total resistance always comes out smaller than the smallest single branch. Your household sockets are wired this way. Let's set the two side by side. In series, there's a single current path, the same current everywhere, the voltage is shared out, resistances simply add, and one break stops everything. In parallel, there are multiple paths, the same voltage across each branch, the current is shared, resistances combine as reciprocals. And if one branch breaks, the others keep working. That last point is exactly why your home is wired in parallel. Let's tackle a network with both. A 6 ohm and a 3 ohm resistor sit in parallel, and that combination is in series with a 4 ohm resistor across a 12-volt supply. Start with the parallel pair. 1 over the parallel resistance equals 1 over 6 plus 1 over 3, which is 1/6, plus 2/6, or 3/6, giving 2 ohms. Add the series resistor and the total is 2 plus 4, so 6 ohms. Finally, the supply current is 12 volts over 6 ohms, which is 2 amps. Kirchhoff's current law deals with junctions or nodes where wires meet. It says the total current flowing into a node equals the total current flowing out, which is really just conservation of charge, since none is lost along the way. If you use signs, the currents at a node sum to 0. It's the tool we reach for to find an unknown branch current, so if 5 amps enters a node and 2 amps leaves down one branch, the other branch must carry the remaining 3 amps. Its partner is Kirchhoff's voltage law, which looks at loops, any closed path around the circuit. It states that the voltages around a loop add up to 0, which follows from conservation of energy per coulomb. Put another way, the EMF supplied equals the sum of all the voltage drops around that loop. We use it to find unknown voltages, and the main thing to watch is the sign, keeping track of each rise and each drop. Let's see it in action. A 12-volt battery drives current through 2 series resistors, 4 ohms and 8 ohms. By Kirchhoff's voltage law, 12 volts equals the drop across the 4 plus the drop across the 8, which is 4I plus 8I, or 12I. So the current is 12 volts over 12 ohms, which is 1 ampere. Then the voltage across the 4 ohm is 1 times 4, that's 4 volts. And across the 8 ohm, it's 1 times 8, so 8 volts. And reassuringly, 4 plus 8 gives us back our 12 volts. Let's pause and test yourself. Can you state Ohm's law and rearrange it to make current the subject? What happens to the total resistance as you add more resistors in parallel? Can you explain Kirchhoff's current law in your own words? And here's a quick calculation. If a 3 amp current flows for 2 minutes, how much charge passes? Have a go before moving on. Now, to power, which is the rate at which energy is transferred, measured in watts. The basic form is power equals voltage times current. Bring in Ohm's law and you get 2 more versions. Power equals current squared times resistance, and power equals voltage squared over resistance. In a resistor, all this energy ends up as heat, which is exactly what we want in heaters, kettles, and filament lamps. Just pick whichever version matches the quantities you already have. Let's calculate one 2 ways. A current of 3 amps flows through a 4 ohm resistor on a 12-volt supply. Using power equals current squared times resistance, that's 3 squared times 4, which is 9 times 4, so 36 watts. And using power equals voltage times current, that's 12 times 3, also 36 watts. The 2 methods agree, which is always a good sign. The Wheatstone bridge is a rather elegant circuit of 4 resistors arranged as 2 parallel arms, with a galvanometer bridging the midpoints. We say the bridge is balanced when no current flows through that galvanometer, and at balance the resistances satisfy a simple ratio. R1 over R2 equals R3 over R4. Because balance depends only on ratios, it lets you find an unknown resistance very accurately, which is why it turns up in strain gauges and precision sensors. Let's find an unknown resistor with it. In a balanced bridge, we have R1 at 100 ohms, R2 at 200 ohms, and R3 at 150 ohms. At balance, R1 over R2 equals R3 over R4, so rearranging, R4 equals R2 times R3 over R1. That's 200 times 150 divided by 100, which is 30,000 over 100, giving 300 ohms. A diode is our first component that behaves quite differently in each direction. It only allows current to flow one way. It's built from a semiconductor PN junction. When it's forward biased, it starts to conduct once a small threshold voltage is reached, and when it's reverse biased, it blocks the current almost completely. For a typical silicon diode, that turn-on point is around 0.7 volts, and one of their most common jobs is rectifying, turning AC into DC. If you plot a diode's current against voltage, the line is distinctly not straight, which makes it non-ohmic. Below the threshold, almost no forward current flows, but once you pass it, the current shoots up steeply for only a small rise in voltage. In reverse, just a tiny leakage current gets through, until, if you push the reverse voltage too far, the diode breaks down. So across its full range, it simply doesn't obey Ohm's law. Let's gather up the newer terms. Power, P, is the rate of energy transfer in watts. A node is a junction where two or more conductors meet. A balanced bridge is the condition where no current flows in the galvanometer. A diode is a semiconductor that allows current one way only, and forward bias is the arrangement in which it conducts. And non-ohmic simply describes any component whose current voltage graph isn't a straight line. Time for another quick check. Can you write down the three equivalent formulae for electrical power? Can you state the balance condition for a Wheatstone bridge? Why do we describe a diode as non-ohmic? And to finish, work out the power in a 5-ohm resistor carrying 2 amps. Take a moment with those. Before we wrap up, here's a reliable recipe for tackling any DC problem. First, list what you know and what you're asked to find. Then simplify the resistor network into series and parallel groups. Choose the right formula, whether that's charge equals current times time, Ohm's law, a power formula, or Kirchhoff's laws. Convert all your units first, minutes to seconds and so on, then substitute carefully and calculate with the unit attached. And always finish by asking whether the answer is a sensible size.
When an object is balanced, in other words, in equilibrium about a pivot, the total clockwise moments equal the total anti-clockwise moments. This principle applies to seesaws, beams, and balances of all kinds. Each moment is force times perpendicular distance, so you set the clockwise sum equal to the anti-clockwise sum and then solve for whatever force or distance you're missing. Let's balance a seesaw. A child weighing 300 newtons sits 1.5 meters from the pivot, and we want to know where a 450 newton child must sit on the other side. By the principle of moments, clockwise equals anti-clockwise, so 300 times 1.5 equals 450 times the distance. The left-hand side is 450, so 450 equals 450 times the distance, which means the distance is 450 divided by 450, exactly 1 meter from the pivot. Time for another check. Can you write down the 3 Suvat equations and say when they can be used? Can you explain why a projectile's horizontal speed stays constant? Can you state the principle of moments and give the unit of a moment? And finally, what's the moment of a 40 Newton force acting 0.6 meters from a pivot? Give those a go.